Okay, we are going to work on solving this differential equation, x double prime plus x equals 0. This is a follow-up to a video where we talked about that and then did some stuff with r's. And we came up with Euler's formula. So I'm going to redo a short bit of that. If I were to let my solution process for this is to let x equal e to the rt, then that means x prime is re to the rt, which means that x double prime is equal to r squared e to the rt. From there, I sub in this right here for x and this right here for x prime. That gives me r squared e to the rt plus e to the rt equals 0. Now I divide by e to the rt, so it cancels out, right? And I get r squared plus 1 equals 0, which gives me r equals plus or minus, when you move it over in square root, you get plus or minus root negative 1, which is plus or minus I. So the first thing I'm going to do is use Euler's formula, which is this right here. So notice that has e to the it. So, well, I guess what I mean is that I'm going to go and I'm going to plug this in the way I would normally plug in a solution to one of these characteristic equations. X is, and I'm actually going to say A1, not C1. Try and not mess that up. So, and you'll see why at the end. I don't want it to be confusing. Make that look like an A. A1 e to the it plus A2 e to the negative it. Now, the a1 and the a2 are just constants the way they would be if I had real values for r, except, well, yeah, they're just constants. They could be solved for. So, what that gives me is, I'm going to use Euler's formula, which says that e to the it is cosine t plus I times sine t. So that makes this first part right here easy to do because it's exactly what I just wrote up there. I get a1, open parentheses, cosine t plus I times sine t. Now let me talk about what the goal here is. The goal is to get a solution to this that is real, right? That doesn't have imaginary numbers in it. And you'll see when I use Euler's formula at first, this piece right here becomes an issue. And I think as we do this, you'll see how we sort of magically get rid of it. So the next thing I need to do is this term, which has a negative I. Now I'll work it out here, but the formula you should just know eventually. E to the negative it, well, that's equal to cosine of negative t. Why is that? Because, did I write Euler's formula? Up here. You could have a's, right? And it would be like having an a of negative 1. So you would get an a there and an a there. So you get a negative 1 here and a negative 1 there. So let me come down here. Or you could just think about it as replacing this piece with a negative t. Then you replace all these guys with negative t's. Anyway, so I get plus ooh, that was terrible. I times sine of negative t. Now, we don't ever write it like this, and here's why. Cosine, like x squared, is an even function. So if I go forwards an amount and backwards an amount, they're both going to have the same height. So what that means is that cosine of negative t is the same as cosine of t. So that means that I can write this cosine of negative t as just a cosine of t. Then sine's an odd function. So what it means is that if I've got a piece out here and a piece the same way back, they've got opposite heights. So that means that sine of negative t is the same as negative sine of t. So what I can do with this guy is write minus I times sine of t. So that's what e to the negative it is. And if you had like e to the negative 5it, it'd be cosine of 5t minus I sine of 5t. All right, so that helps me down here. I get plus a2, which is just a constant, times cosine of t minus I sine of t. And now I'm going to group like terms. Notice I've got a color-coded. I've got a cosine here and a cosine here, right? This first one has an a1, the second one has an a2. Everything's positive. So I can write that this is equal to a1 plus a2 times cosine of t. Now, the next ones, go here. This is sine t with an I on it and a negative. And this is sine t with an I on it and a positive. This one's got an a2, that one's got an a1. So what I wind up getting is plus I, open parentheses because I'm going to factor that I out, times a1 minus a2, and then times my sine of t. Now, you may say, this doesn't help, because I still got this I here. Wouldn't the whole point of raising this to the converting it with Euler's formula, wasn't the whole point of that to get rid of imaginary numbers? Look, I still got this imaginary piece right here. Well, if you are careful about what you let a1 and a2 be, then I got distracted. I don't know where I was, but I think I was saying that it is not real yet, right? I got an a1, a2, a1, and I got this I here. But I can very carefully choose values of a1 so that I get real constants that don't have any imaginary pieces in them. It comes back to what we call conjugate pairs. So conjugate pairs are, I'm just going to give you 3 examples, and I think you'll see what it is. 3 plus or minus 2i. So what I mean by that is 3 plus 2i and 3 minus 2i. Another one, 10 plus 5i and 10 minus 5i. Those are conjugate pairs. And the next one would be negative 3 plus I and what I'm going to take, negative 3 minus I. So all I need is for the first number to be the same for all of them, and then the first number to be the same for all of them, and then the second one to be plus or minus versions of each other. So if I take a1 and a2 to be conjugate pairs, then I will get a real number out front of the cosine and a real number out front of the sine. Let me show you. I will do it with these first two, 3 plus 2i and 3 minus 2i, and 3 minus 2i. So let's take a1 equal to, and it's with this equation right here, equal to 3 plus 2i, and a2 equal to 3 minus 2i. Watch, when I do a1 plus a2, it's real. a1 plus a2, well, that gives me 3 plus 2i plus 3 minus 2i. The 2i's cancel, and I get 6. You can imagine, instead of using a 3, I could have used a 4 plus 2i and a 4 minus 2i. Then I would have gotten an 8. I could have used 100 and 100, and that would have gotten me 200, right? So I could have used negative 7 and negative 7, and that would have given me negative 14. What I want to convince you of is that I can get that to be any number by being creative with my conjugate pairs. So that means that this could really be any number, and I'm going to call it C1. So I'm going to rewrite this equation down here. I need a little bit more space. as x equals C1 times cosine of t. This is hard to explain. It's hard for people to understand when we're in an actual classroom. But the bottom line is that I can choose complex A1 and A2 to make it so that when I add them, I'm going to get a real number. Okay? And that's my C1. Now, let's look at what I get for this piece right here. Well, if I take, and I'm using these same conjugate pairs, I times A1 minus A2, well, that gives me I times 3 plus 2I, and then minus 3 plus 2I. That's the negative version of this. And look, these real parts inside of the parentheses go away. And I'm only left with inside of the parentheses a positive 4I. So I have I times 4I. Oh, snap, that's 4 times I squared. Notice, with this I piece out front, the problem would have been anything that had a real component to it. And since I chose conjugate pairs and they're subtracted, those two pieces go away. And I'm left with just the imaginary part of it. So I get 4I squared, and that gives me negative 4, right? And what I want you to see is that just like I could choose the 3 to be any number and get anywhere, 6 for example here, I could choose this 2I, the plus or minus piece, to be anything, and I could get to any number here, right? I could choose 5I and minus 5I, and that would give me minus 10, I think. I could choose negative, I could flip them in the order in which I'm subtracting them, right? Choose this A1 to be the negative one, and this A2 to be the positive one, and then I could get a negative here, which would give me a positive after I get the 4I in. So what I'm trying to convince you of is that I can, if I choose these A1 and A2 constants to be complex conjugate pairs, then it will get rid of the imaginary component of this equation right here, and I can call this half over here plus C2 sine t. And that is the solution to this thing. And it should make sense. It actually matches what we did a really long time ago, which was to say, oh yeah, duh, sines and cosines. Those are the answers. That's a thing for which the derivative is the second derivative takes me back to the negative version of the original equation. So our intuition is verified by using Euler's formula. And now we can go and we can solve ones that you can't do with intuition. And we can use Euler's formula to do that. And I'm going to do that for, I think, 2, maybe 3 in one more video. Bottom line, this guy, Euler's formula, solution, that. Oh, actually, I'm going to say one more thing. So you may be like, man, that's a lot of work to get to whatever I did there. Well, I'm going to tell you that from here on out, if you have x double prime plus x equals 0, here are the steps that you can write. R squared plus 1 equals 0. R equals plus or minus I. And then this step, bam, you can go straight to x equals C1 cosine t plus C2 sine t. Once you get the imaginary part here, you can go straight to the solution. You don't have to do all this crazy algebra with imaginary and complex and Euler's formula. Euler's formula is why we can do that, right? But you can just bump straight from here to there.